live on YouTube. Fire now. Okay, 11 o'clock on a Sunday morning. Good morning, our special 5th Sunday session. Welcome to Chai and Why. At Chai and Why, during the pandemic, we've tried to bring you online sessions. And guess what? The show must go on. Last night at 11:40, yesterday we were practicing, we were setting up the experiments. 2 of our team members, right, got a message that some student had been detected COVID positive, and because they were primary contacts, they would have to quarantine. This message came at 11:40 last night. So the 2 people, Divya, who handles our Facebook, he's actually doing it from the quarantine place. Surbhi, thank you so much for setting all this up. I hope you're watching this. She set many of the experiments up, but she's under quarantine. I'm very happy to say that we have Krishna to help us here today, and Kiran, where are you? Kiran is somewhere there. We have Kiran as well. Kiran will help us. So we've had students step in, and Abhinav as well to help us with experiments today. Krishna is a PhD student who works on light in very small areas, and he's from Uttarakhand. He's come here. Abhinav works on making structures which are very small that interact with light in very interesting ways. He's also a PhD student here. Also from Uttarakhand? Yes, the 2 students from Uttarakhand are here. And from Haryana, we have Kiran. She is just joined. She's a first-year student. She'll figure out what she wants to do, but she's going to work with, most probably, with light. Light is such a wonderful thing. Now, those of you who watched us last time, you know that we did some experiments showing you various properties of light. We said that light was a wave, and because of that, light behaved in very strange manners. When you send it through very small holes or slits or things like this, it went around wires. That was phenomenon of, or edges. You had phenomenon like interference and diffraction. That's of course one aspect of light. But light as a wave has some amazing properties. And one of them, which we'll explore today, is polarization. And with polarization, believe me, we can do some really cool experiments. In fact, we'll go slowly, but let me show you some of the very funky stuff we're going to do there. Just preview here. Just look at this picture. Look at this. These are just some.
Arnab, you are not audible. Krishna should be closer to you.
Scotch tape. These are just some pieces of Scotch tape. Yeah. Look at the colors of this Scotch tape. And I'm just going to turn this. And look how magically, almost magically, the colors change. Okay, we'll be doing a lot of this kind of fun stuff. Okay, but before that, I'm going to hand it over to Krishna and others to help explain what's going on. Please remember that the only way we know the questions from you is via chat. So please put in your questions in the chat box on Zoom or YouTube or Facebook, wherever you're watching, and we'll try and take them up here or answer them in the chat or something. So please keep telling us. And also tell us, we have no idea. Are you school students? Are you college students? Are you just, watching for fun? Well, I guess everybody's watching for fun. But okay, over to you, Krishna. Yeah. I'm going to go and monitor the YouTube.
Yeah, thanks, Arno. Yeah. Hello, everyone. I'm Krishna Joshi. I'm a research scholar here at TIFR, and I'm working in this nano-optics and imagescopic optics laboratory. So in the first part of this previous webinar, we have seen some wonderful experiments like total internal reflections, interference and diffraction, and etc., which explain the wave nature of the light. We have seen all these things. But today here, what we are going to talk about, we are going to explore some other property of the light, which is this thing in this year. We are going to talk about some many other properties of the light. So before starting this point, so especially now.
Oh yes, there was an experiment from last time which we forgot.
Yeah.
Oh yes, yes.
Yeah.
There's one very cool experiment which is actually a very simple experiment with a lens. But yes, Krishna, why don't you show it to them before we get to polarization?
Oh yeah, but before I want to just give some basics of the light.
Yeah, yeah. Yes,
okay, I will come to that point. Okay.
Yeah,
so okay, yeah. Okay. So today here we are going to talk about that. We are going to explore some other properties of the light. Especially Arnav said, like this thing, we are going to especially talk about the polarization of the light. So before going to start this session, so I will talk about some basics of the light. I will start with this some basic property of the light. So let us start with a basic question: is that what is light? And another question is that why don't we see the objects in the dark when there is complete dark? Why we don't see the objects? So the answer of this question is very simple. The answer. So you will learn that the answer of the first question is later, but the answer of the second question is that it's very simple. It is the light. Because of the light, if light is there, we see the objects, and if light is there, we don't see the objects. But have you noticed is that light has vital role in the human survival? Because of this, we can't even we can't expect the survival of the human, but it has. So can you imagine that what is the main source of the light in the earth? This is sun. Sun emits all type of lights, and if you combine all these lights, all the emission from the sun, you see that it can form an electromagnetic wave. So let us see what is electromagnetic wave. So here I have an electromagnetic spectrum. You can see here this thing. So it spans from the radio waves, which is very low frequency radio waves, and from this radio waves to the X-ray. X-rays are very high frequency range. When you're going from the left to right, and you see that the frequency is continuously increasing. But in a very narrow region, in the middle of this spectrum, you can see there is a very narrow region. This is what you call the visual light. And human eye can only detect that light, and it consists of beautiful 7 colors of the light. Okay, so that's about the electromagnetic spectrum we have. So this is all about the electromagnetic spectrum. Now let us talk about some other properties of the light. When we first learn about the light in school, we were taught that light always travels in a straight path, in a straight line. Okay, so then what happens? But sometimes what happens is that some interesting things happen when light passes through one medium to another medium, or it hits an object or something like that. So let us so before going to the some before going to the some other properties of the light, what we are going to do, we are so I'm going to interrupt Arnav first. So Arnav, have you noticed in the last webinar is that we forgot something mentioned in that we forgot something.
So let's just do the let's do the experiment.
Yeah. So in this, so we forgot to mention that the geometrical part of this topic. Okay, the geometrical parts. So what we so in this case,
so here we have a very simple. It's almost like a school physics experiment where we have a light source. Our light source is a little laser pointer. Let's turn it on. Okay. So the laser pointer, we have a lens, a convex lens.
Yeah, this is a Plano convex.
Plano convex lens, and we have a screen where you can see the beam spot. The spot of the beam, the laser is getting focused on the screen.
Yeah.
Now, one thing is, what do you think will happen if we move this laser left and right? Are you moving it left and right or up and down? Left and right. We'll move it left and right in this, and let's see how the spot should change. So do you think, how do the spot change if I move it left and right? And just to show you that the laser, we are actually moving the laser, we put a little ruler like thing marks below, so you can see that we're actually going to move the light source. Okay, and watch how the thing changes. You want to guess? You want to take a guess in your minds? How do you think this light spot will change? Is it also going to move to the left if we move the laser to the left, or move to the right? Will it move the same way, the opposite way? Okay, why don't we do the experiment?
Yeah. So what I'm going to do, I'm going to move this laser pointer in this left and right direction, and let us observe this what's going on there spots on this spot. Okay. So moving to the left, can you see some changes here? Okay. So now moving to the right. Right now my this laser beam is falling at this one end of this thing, planar convex lens, and then you can see that still I can see the spots is at the same position as earlier.
Okay, but you know what? I'm going to take a pen or something and mark where the spot is so that people know that this is where the spot is.
Yeah, let's see.
Okay, I'm just going to keep it fixed here. Okay, now you move.
Yeah, I'm going to move in opposite direction. No, I think the screen is.
Wait, the screen is. Sorry, the screen. Okay, just look at the spot. If I touch the screen, it's going to move.
Yeah, I can use this thing as a mark. We see that the spot is not moving at all. Okay, so we have clearly seen that the spot is not moving at all. So why this is happening? So what do you expect is that when I'm moving this laser pointer and then it is moving him up and down, what we should first we should expect is that it should also move in this screen. But this is not happening. Something is there wrong in this is something is wrong here, or it is actually happening. So in order to understand this behavior, let us see some kind of properties of this light, the refraction of the light. So what happens? So let me just tell you about this plano convex lens, this lens. So as you know, it has a name plano convex lens. So one side of this has a plane, and the other side has this spherical surface. Okay. So what I'm doing here, I have a laser pointer here. I'm sending the light from here, and looking the light spot here. So I'm putting my screen over here and then looking this here. So we see that when I'm moving this laser pointer in this direction, we see that this spot is not changing at all. So if I move the light here and here and here, I don't see any change in this direction. I don't see any kind of movement in this direction. So why this is happening? So it means so as you can you can imagine is that what is happening there. You can see is that something light is bending from here. So it is something light is going like this. Okay, this process is called refraction of the light. It is. So let us first understand what is refraction of the light. Okay, so this is a picture where you have these two mediums. Okay, as we know is that when light travels from one medium to another medium, what happens is that it refracts the light. It bends the light, as you can see, and it follows the laws of reflection. Okay, so then what happens? The reflection law is the Snell's law. So when a beam is incident from this medium one at angle theta, and then when it is emitting from this second medium, when it is passing through the second medium, it follow this angle of refraction, and then finally you can calculate this theta 2 from this Snell's law. Now, if I put this theta 2, theta 1 is equal to 0. If my wave is just falling normally onto the surface, so what will happen? Then my theta 2 is become also 0. So it means it will just pass through this thing. Okay, it will just pass through. It will go in this straight line. Okay, so now let us apply these two things to the this plano convex lens. So in case of this plano convex lens, what I have. Yeah, so I have two faces. I have two surfaces. One is plane surface and another is this plano convex surface. So when my light source is here, what is happening? If you apply the law of reflection, the Snell's law of reflection here and here at these two surfaces, we see that this is almost incident or at the normal. It is there. So it means it is just it will just directly pass through there. It will not bend at all. But what happens when this laser screen is when my laser pointer is here? What happens? The light is going in this direction, but at this plane surface, what is happening? It is falling normally, but as it's passing through this other surface, what is happening? It is bending. It will bend because of this law of it. You can take this as a this take home work. You can take this as you can calculate is that whenever you calculate these laws of reflection from here to here and then finally, then you will get every time that light ray will meet at this point. It will try to join at one point. Okay, so this is happening when my laser point, I'm moving the laser point in this direction, and in this direction, it basically trying to join every time it's trying to join this a particular point. Okay, so this is what we called refraction refraction of light.
Okay, so now how you know how a Plano convex lens focuses the light at a spot. We had sort of forgotten to do this experiment, a very basic experiment showing you how light is refracted at the two surfaces. Thanks so much, Krishna. Let's move on then with today's experiment.
Yeah, okay. Yeah, okay. Okay, so we have seen that the reflection of the light by using a plano convex lens. And have you noticed one thing about this process? In order to explain all this process, we just use the ray diagram and everything. We didn't use anything else. But wait, so there are some experiments which cannot be explained by the this ray, this just by drawing this ray. So there are, so in the previous webinar series we have seen is that there are some experiment light interference of the light, and this we have seen which shows the wave nature of the light. We found that we found that we can only explain this experiment if you assume that the light is a wave. So yeah yeah so so I need one okay. So what I'm going to explain. Yeah, just let me start. Okay. So as we know that the light is light has a wave nature, and then we are going to explain that what are the waves and what is these things. So here I will draw. Can you explain this thing?
Go ahead.
Yeah.
So this is just a very simple demonstration of waves. We thought we would show you how waves are on a string. Now, two people catch a string and you shake it. Come on, let's make some waves. Okay, you can see that the string is going up and down, and there are some waves on the string. Of course, remember, light waves are not like this. Light waves are electromagnetic waves. There is an electric field and a magnetic field, but there are some things which we can, it's very difficult to understand some concepts. We can try and make simple analogies. They're not correct. Please remember, they're not correct, but they are simple and help you to understand how things are moving up and down.
Yeah.
Okay.
Yeah.
So in a wave, make some waves, please.
Yeah.
In a wave, imagine this is light propagating in air. There are waves. You can see that there is some ups and downs on the rope. There is some distance between them, which is the wavelength. Okay. And you can make, of course, the wave vibrate in two ways. You can make the wave vibrate up and down. That's now the wave vibrating up and down. And you can also make waves if you move this rope left and right.
Yes.
So you can move it left and right. Okay, one of you hold it steady, the other one move it much easier. Yeah. So now you have waves which are moving left and right. But there are lots of different kinds of waves you can make. You can also move the wave, you can make it move in a circle. Right? You can also you can see when the rope is moving in the circle, the middle point is actually not moving. There is a beautiful waveform with a node in the middle of the rope, and the rope is actually moving in a circle. So there are circular waves, there are sort of what are called linear waves. There are lots of different waves you can make even on the rope, and light also has many different kinds of waves. Okay. Now, in a light wave, these electric and magnetic fields are always at they're always at right angles to each other. and to the direction in which the wave is moving. So if the wave is moving in a particular direction, now out here the red, which is going up and down, represents the electric field. The magnetic field is at 90 degrees to this. This is moving in the sort of horizontal way, this is vertical, and that's how this electromagnetic wave is. Now the orientation of these electric and magnetic fields in the wave, now it could be this, it could be moving up and down. After a little bit it could have turned and be moving, another wave is moving left and right, or the other wave is moving slightly at an angle. So there is nothing saying that it has to move up and down. And in general, if you take the light from a bulb or a fire or any source, the light is generally moving, these electric and magnetic fields are moving in all directions. They are at right angles to each other, but there's no preferred orientation. However, you can make light in which these waves have a preferred orientation, and that is polarized light. Okay, so should we sort of demonstrate this, or
yeah.
So hello, as Krishna just explained, that light is a wave, and it's not just a wave, it's a wave with direction. And no, we are not talking here about the direction of propagation. We are talking about the direction of vibration of electric field. So this direction of vibration of electric field is what gives the polarization of light. So what is polarization, and is it really important to study this, and does it makes any sense in day-to-day life? We will answer all these questions shortly, but first let's have a fun experiment. So here is our experimental setup. Okay. So this is a simple plastic looking sheet, which is not actually a plastic sheet. We are putting it here, and then we are taking one more sheet, similar sheet, and we are putting it on the top of this, and we can see some light is coming out of it. But now when we will rotate it, keeping the first one steady, we will rotate the second one. So here we go.
Very bright.
It is very bright, and here it is very dark.
Not so bright.
So we can see it there actually.
You can't see it there.
Okay, so no.
Okay, you can.
Okay, so here we can see it on the screen. It is very bright, and at this point, it just disappeared. So why it disappeared, and why? Because it's just rotation of the second sheet, it is disappearing and it is appearing again. What is happening actually? So these are actually not simple plastic sheets. So the question is, what is the property of the light that is passing through these sheets? And the second question is, what is the properties of these sheets? Which are what are the properties of the sheets which are not allowing the light to pass through? So this reminds me of something. When I was in school, on Wednesday and Saturday, we had to wear this white uniform, and there used to be a teacher. What he used to do, he used to check the uniforms. So he won't allow you to go in class. On Saturday, he won't allow you to go in class if you are wearing some non-white uniform. So these seats are kind of this teacher who is checking the uniform of the light. So what actually is happening here is, as we just said, that light has the vibration of electric field is known as polarization. So the polarization of light, the vibration of electric field can be up and down, and this left and right. So this polarization, our teacher who is checking the uniform, it has a this transmission axis. So it will allow only the polarization up and down vibration to pass through this. And here we will get this light which is polarized in up and down direction. Now, suppose that there is one more teacher who don't know that it's Saturday, and he thinks that you need to wear a non-white uniform, and he's standing here uh, checking uniform again. Then he will eliminate all those students as well, so no student will be able to pass. So this is what is happening here. We are using another polarizer which has the direction of transmission axis which is perpendicular to this, so it will not allow even these vibrations to pass through. So this way the light will be completely blocked. But if this is in this direction, the second polarizer has axis in the same direction, then it will pass. So that's why rotation affects the polarization.
So in one case, the second one is this way, and this person can pass through this. And you're saying in the other case, when you move it, it's this way, and this one cannot pass through.
Yeah. That's how it is. So to make it, so to physically realize it, we will do one more experiment, which is analogy with this rope, the waves we just generated. So we can do how. So this polarizer is basically this kind of fence that will allow that has, like, we can say that this is the transmission axis, so it will allow only these vibrations to pass through. So let's do the experiment. So here we can see that we will vibrate the string up and down, and it it should pass. So we can see the waves on both sides of the slit, up and down. So maybe we can. So here we can see that on the both side of the slit, the waves are forming. But when we do it left and right, we can see that on this side, it is not moving. The waves are only one side of this slit. That is, the waves are not getting transmitted. It is not allowing the waves to which have vibration in this direction to transmit. So let's do this with the circular case. What will happen if we will rotate it circular? So we can see that some of the component is passing and it is not vibrating that much. It is vibrating up and down. So the component, it will basically, from the vector algebra you have learned that we can resolve a vector in this perpendicular coordinates, and only one of the component will pass through. So that's how it is.
So now let's turn this. Yeah, turn your fence.
Okay.
Okay, so when they were moving it circularly and the fence was vertical, only the vertical wave was passing through. So Krishna is moving the moving the rope in a circle, but only the wave which was moving up and down was being able to pass through. So Krishna moved it in a circle again, and let's see what happens. Now I hope you can see on the screen that only the wave which is on Kiran's side, the rope is actually moving left right. It's only one component that's passing through. Okay, so this is, and if he moves it up and down, oops, if he moves it up and down, that wave does not pass through. You can, just come back. On the other hand, if he moves it left and right, that wave passes through. Now, please remember that this is really a very bad analogy for electromagnetic waves. They are not like waves on a string, but this is like a very simple example and analogy, which is just to give you, we didn't want to write equations and go through the whole thing. We just wanted to make a very simple example. This is not correct, okay, because this will not be able to explain this, what happens when we rotate things and how the brightness changes. That all you can't explain with this. But at least you have the idea that you have something like a fence which allows selective parts to go through, and if it's not in the right direction, it will not go through. So that's the only purpose of this analogy. Okay, but let's do some more fun experiments.
Okay, so now we have seen that we can move the rope up and down, left and right. So this kind of vibration in a specific direction is known as the linearly polarized light. Now the other thing we did was moving in the circular direction, and it It is the kind of this kind of light which has electric field vibration in the circular motion are known as circularly polarized light. And we can have vibration in random directions, and that light is known as unpolarized light. So what a polarizer can do, it can change the unpolarized light into polarized one, and it can further detect the second polarizer that we use. It can further detect the whether the light is polarized or not. So as we know all these things, let me tell you one more thing, that the light from the laptop screen which we see is actually polarized, and even from some of the mobiles, not all mobiles, but some of the mobiles. So let's check it. So here we are having this polarizer, which we are placing in front of laptop screen, and you can see that it is quite bright. Okay. So let's see with a bigger polarizer.
And turn the polarizer.
Oh, and it becomes dark.
So the light coming from the laptop screen is actually polarized. So depending on how I turn the polarizer, it will block the light at a certain direction. Okay, so this way the light doesn't go through. You turn it, the light goes through. If you turn it again, the light will not go through, things like this. So this is a big polarizer. We can also do it with a smaller polarizer, where you can see as I turn it, it's dark, it's light, it's dark, light, dark. Okay, so the screen from a laptop is polarized, and in fact, if you have a high-end mobile, many of the mobile screens are also polarized. So here is a mobile phone, and there you can see the mobile phone. Can you just center it in the picture? Yeah, there, very good. And if I turn it, oh, there you go. It's dark, bright, and it should again go dark. Somewhere there it goes dark. Okay, so this is also polarized light. Okay, what else can we do with it?
Okay, so now that we have learned this much about polarization, and we know that light is a wave, and in our day-to-day life, it passes not only through air, it passes through different mediums, which has some refractive index and which slows it down and bends the light. But there are also some materials which acts differently for different polarizations. Let's have one more experiment about this. So these materials are like the teacher who sort the students on the basis of different uniform. Okay, you are wearing this uniform, go this way, and you are wearing this uniform, this go this way. So let's see how this is sorting the light. So first of all, we have this crystal, and its name is calcite crystal. So this is a simple looking crystal though, but it has some special properties. So let's put it.
By the way, I really wanted to thank one of our volunteers who used to be with Chayanwai, Gargi. She used to be in Mumbai with Chayan and was to volunteer for Chayanwai many years back. She is a geologist at IIT Roorkee, and this is one of the nicest gifts I've ever got for giving a talk. It's a crystal of calcite, naturally occurring, formed over millions of years in the earth, and it has some wonderful properties, optical properties. The strangest thing is, once light enters this, the two polarizations can travel in two different ways, and that gives you some beautiful effects. So can we see this? Is it this one?
Yeah.
Yeah. So here you see the word calcite is written here, and I'm going to keep this block. And can you see double letters? And I'm going to rotate this. I'm going to rotate this. Do you see how the calcite is moving? The image of the calcite is moving. Now it's on. So there are two images being formed. This phenomenon of double refraction. This is double refraction. It's also called birefringence. And these two images that you see, So the word calcite, you're seeing two images of it outside, are because this sort of separates two rays out. And it's more fun if you put it at a corner. Let's put this at you see this picture, it has a little corner. We'll come to the drawing later, but just see this little corner. See the corner through this. And I'm going to turn this again. Let's turn it. Now this side is aligned, but that side is split. Now that side is aligned, this side has split. Here, both of them are different. So you see, it's actually bending light in two different directions in two different ways. So this is a crystal that has different optical properties in different directions. And let's look at what is the polarization of this, right? So let's put this. You can put it this way, right? This way. Yeah. Put it this way. Yeah. Or is it this way, which is better? Okay. So what we have is we have a little laser pointer. The laser pointer hits a mirror, and the mirror just bends the light by 45 degrees. It goes through the calcite crystal, and it gets focused again onto a screen. And the two beams of light, you probably can see on the screen that there are two spots. There are two spots on the screen. Will you show them the whole setup? Yeah. Yeah. So light source, mirror, goes through it. You can probably even see the two beams inside the. Yeah, you can probably see that there are two beams inside the. There's one laser beam coming in, but there are two laser beams coming out of the crystal, and they are focused. And you see these two spots. Now it's very bright over there. So what we'll do is we'll look at the thing behind the, and we'll take one of our polarizers. We have these polarizers with us. We'll take one of the polarizers and try and see if the beam coming out is polarized. So I'm going to put the polarizer there and try and rotate it and see what happens to the spots. You see, one of the spots is gone. One of the spots is not being lit through. Here we had both the spots. The lower spot disappears. At some other point, the upper spot disappears. The lower spot is getting through. Over here, the upper spot is gone. The lower spot, I mean, is not visible. The lower spot is going through. Now both the spots are going through. I'll turn it again. At some point, again, the lower spot is blocked. Right? So the two beams are actually polarized differently. And this is the phenomenon of birefringence in this material called calcite. Okay, so that was one way of making polarized light. You can use some special materials which are have the property of sort of taking an unpolarized beam and making two differently polarized beams out of it. So that's like a crystal of calcite. Okay, let's do some more experiments. So Abhinav, you're going to take over?
Yes.
Lovely.
Thank you.
Go ahead.
So we had seen some more experimental setup. Yes. So we have seen some examples of how to make the light polarized. So like we did with a calcite crystal, and we used some polarizer sheets there. But these things are not generally available at homes. So I will show you very inexpensive way to make a polarized light, make the light polarized, and you actually see it daily. So it is nothing special. It is just a reflection from a surface. Okay. So this is my setup. I have a green laser pointer, and I have this plastic block, and I can rotate this plastic block. If you see, there is the reflection coming from the block, and I can, if I change the angle, the spot will move. But there is, we can check the polarization properties of this spot. So suppose it is at this angle, and I put a polarizer in front. If I rotate it, not much change is there on the intensity of the spot. But if I increase the angle a little bit more, you will start seeing that this has some polarization effect. So the intensity changes as I rotate the polarizer. If I increase it even further, so again you will see some polarization effects. And actually there is one particular angle, if you go at that, the reflected spot almost disappears, like here. Okay, so this particular angle is also called Brewster's angle. So let me try to explain it using a diagram, what exactly we just saw. So we have a laser falling on a surface, which is our plastic block. It has two different polarizations initially. Actually, it is unpolarized, but it has two components also present. So one is this one, other is going inside the plane. The direction of the polarization is inside the plane. When it hits the surface, some part of it gets inside the plastic block and some of it is reflected. So at a particular angle that I told you about, that is called the Brewster's angle, only one of the polarization component gets reflected. Uh, Transmission, in the transmission we have both, but in reflection we have only one. So that is why we were able to extinguish this spot using a polarizer here. We are able to make it disappear.
I think you have to be at the right angle. It's probably moved a bit.
Yeah. Okay, but yeah, you see the point. So not so we saw that it is going away for a particular angle, but you will need actually extremely flat surface if you want to extinguish it completely, and also the angle should be very perfectly matched. But even for the angles near this Brewster angle, there is some amount of polarization. So we are able to reduce the intensity of the light even at for other angles. Okay, so this fact about the reflections and uh, how uh, how the polarization is generated by the reflection uh, actually can help us in many ways. So people, so there are something called polarized sunglasses, which yeah, which can uh, which can help us protect our eyes from the glare, and even the sailors on the seas, they use the polarization, these polarized sunglasses, because they were able to reduce the reflection that come from the surface of the sea, the surface of the water. So one such demo we are going to show you how we can make the reflection disappear. So I have a this small plastic container and some water is there, and I've written something on the bottom of the container. And if you see, there is a, you can see a tube light reflecting from the surface. That is the tube light in the room. And now you cannot see the text. And I will
wait, you moved it so you can see the text.
Yeah.
Okay, but there's the tube light. You see the reflection of the tube light.
Yes.
Okay, you see the reflection of the tube light. And now we have the polarizer. We're going to bring it in front of the camera of the. Okay, so we have kept the. Where's the? Wait, let me just get the. Yeah. Okay, very good. So now we are looking at it through the polarizer, and I'm going to turn the polarizer. Turn the polarizer. Wait, where's your? Oh, the camera. Okay. And there, you see, at a certain angle, the reflection completely disappears because the reflection is polarized. And as long as my polarizer is at 90 degrees to that, it will not go through. And you see chi and y clearly written at the bottom. If I remove it, there's the light. If I put it there, it disappears. It's just that the polarizer, if I turn the polarizer, so effectively what I'm doing, I'm taking this polarizer and turning this. I'll do it right here so you can see the polarizer being turned. There. At some angle, it disappears. There you see the light. You see the light, and it disappears. Okay. So the reflection from the water is strongly polarized, and this is true from reflections from plastic, reflections from pretty much anything. Reflections from a table, from your floor. Most of the reflections we see in the world around us are polarized. And that is why most cameras, one of the easiest things you will find if you have a sort of DSLR or some camera which has a lens, they often come with a polarizing filter in front of it to eliminate these reflections that would otherwise arise from various surfaces. So you can also generate polarized light by reflection from a surface. And at a particular angle, for some surfaces, if it's a very flat surface, at a particular angle, the light is completely polarized, and that's called the Brewster angle, which Avina was trying to show you in an earlier demonstration. Okay, what's next?
So next is the Scotch tape.
Okay, so now it's time to have fun.
Aruna, you are using too many of these polarizing sheets. Where do you get them from?
How do you get polarizing sheets? Okay, so this is something which I think I should tell you. So I guess you can go to a nice shop which sells physics equipment or something and buy polarizers, which are sort of super expensive, probably, I don't know. But the way we get polarizing sheets, especially dark polarizing sheets, is from the junkyard. So every time somebody throws away a monitor or a laptop.
Arnav, your voice is low actually.
Yeah, because my mic moved away.
Yeah, and it's splitting.
Just come here. Okay, can you hear me now?
Yeah, it's okay.
Okay, so every time somebody throws away a monitor or a laptop screen or something, we pick it up from the junkyard. Now, if you open a laptop screen out, you will find that there is a piece of glass. This is a piece of glass. And this piece of glass, you take it out. Be very careful, it's sharp. This glass, remember we said that the light from a laptop screen is polarized because there is a polarizer. And you see this black little film. There's a film stuck on it that if you have enough patience, you can slowly rip off. You can slowly rip the film off. It's got some really sticky glue on it. It's very difficult to get the glue off fully. We've tried to wipe it with, alcohol and acetone and whatever. It's very difficult to get the glue off. You peel it very carefully. If you peel it too quickly, it'll break. You're going to be very careful. It's a glass sheet. So this screen had this polarizer in front of it. Okay, so we removed these polarizers from junk monitors. And once you have a big polarizer like this, it's great fun. What do we do with it? Let's see. So I have a source of unpolarized light, which is a overhead projector, the good old overhead projector.
Should we just show them first the polarization rotation?
Yeah, sure.
Solution.
We can do it in this. Yeah. So there is one with the small one.
This one. Windows needed.
Okay, so we have just a piece of cardboard on it to create a spot of light. There we go. This is unpolarized light. Yeah, right there. Okay, look at it on the screen then.
Okay, so I have
to look at all kinds of stuff which is polarized.
So can you focus here? Yes, I have these two cylinders. One has.
So can you just turn the lights on so we can see the cylinder?
One has water. Yeah. So one has plain water in it, and one has a sugar solution. It is almost saturated sugar solution, and we will see what is the difference between these two in this experiment. So first I have a white light source, then I put a polarizer on top of it, and I will put this cylinder on the top, and then I will see through the other polarizer what happens. Okay.
Is this water?
Yes. So as
water, we are just transmitting light, polarized light through water.
Yes. So that
and the transmitted light, nothing is happening.
Yeah. So actually, that's just the intensity is changing because the light is polarized, and we are using a polarizer to see the this outcoming light. But if I change it to the sugar solution, you will see some interesting colorful thing. So at this angle, this is the color. As I keep on changing the angle,
it's just very bright.
It's
extremely bright.
Yes.
I'm gonna reduce the intensity a bit.
So
okay, it's yellowish. Wait, we should be able to see very nice colors if you hold it correctly.
The camera is there.
It's actually just too bright. Ah, there.
So actually, as I rotate the polarizer, the color of the solution will keep looking different to us. And I will try to explain it using a small diagram. So we are going to learn two new things about the polarized light and the how the polarized light interacts with, or what happens to it in some medium. So we have this on the right side, we have the source of unpolarized light, that is the white light source. And it has all the colors. I am showing three of the colors, blue, red, and green. And arrows are denoting the direction of the polarization. So they are pointing in all the directions, which means the light is unpolarized. If I put a polarizer of which has this axis along this direction, all the colors will come out polarized along this direction only. And then when it passes through the sugar solution, this solution has the property of rotating this polarization. So all three will get rotated, but how they are rotated will depend on the uh, color of the light. Okay, so this property, this color dependence of this effect of the medium, that is called the dispersion of the medium. So passing through this dispersion of the medium, suppose final in the end I get this green aligned in this direction and red and blue along the same directions, which are perpendicular to the green. And then if I place an analyzer parallel to the polarization of the green light, I will only be able to see the green light, and red and blue will not pass. But if I rotate this analyzer, I will be able to see red and blue also. So as I keep on rotating the analyzer, different color combinations are going to come out. And that is why we are seeing this colorful solution when we see it through the polarizer.
You want to try this one more time? I think I have a little. Okay, now you see colors in the sugar solution. As I turn this, you can probably see sometimes it's very bright, but it's because it's directly looking at the light. You see the colors are changing slightly. You see some wait, here, yeah. Oh, there we go. No. Oh, there. It was bluish, greenish, pinkish, yellowish. Okay, so I hope you can see these colors on the screen. But of course, we can do more stuff. No? Why don't we put some more stuff between this? Why sugar solution? Let me just remove this one. Let's just get the sugar solution and all this up. I don't want to spill sugar. But let's try. Where's the other big polarizer? Ah, there it is. So let's take objects which we find at home. For example, a plastic glass. So here's a plastic glass that I'm putting on the polarizer, polarized light, and I'm putting another sheet on top. Now do you see this plastic glass is colorful? And these patterns will change. Keep the lights on, please. Please keep the lights on. Or, yeah, because otherwise it's too bright over here. Keep the lights on. Okay. So you can see this was a plastic glass, but we can actually do much better with other objects. And one simple thing to get is go to a geometry box. And if you go to a geometry box and take a simple set square, that's a set square. Now the set square doesn't look, but there's still a polarizer. There's nothing great we can see. But now let's put the second polarizer. See some colors here. Let's try and turn this. You've got to be here because your mic is. Just a minute. Just a minute. Turn this here. Yeah. Okay. Yeah. Sorry. And now the 4K plane also. Let me just focus it. Yeah. Okay, are you going to look at it here or on the screen? I think I can take it on the screen as well.
It's not focused. Yeah, you need
Yeah,
to keep on continually doing it. Yeah, this is focused.
Okay, now it is focused. And hopefully on your screen, you can see a very colorful set square. And as I move the polarizer, you will see that the colors change. And you have a different set of colors. A different set of colors. Oops.
Don't move the object.
Yeah, it's this sellotapes are getting stuck here. Okay. And these colors change. Actually, your eye sees the colors much better. Okay, let's add more set squares. Let's put
Focus adjust karna Krishna.
another one.
Focus adjust karte rehna.
Look at this. Here are two set squares. Again, what you are seeing, the colors are actually due to stress. So when they make these plastics, when they are sort of made from a melt, the melt solidifies, and there are residual stresses in the plastic. And these images that you see are actually images of the residual stress. Because of the stress, the plastic is slightly anisotropic. It sort of bends the polarized light slightly differently, and you see different colors depending on the position of the two polarizers. Let's put a protractor on top. Well, we just put the protractor by itself. Once you see the protractor, there's a protractor under polarized light. Isn't that beautiful? And again, we can move it, and these patterns will change. So you can always make some art by just putting a whole bunch of plastic objects. So that's a whole bunch of protractors and set squares. And if I put a polarizer on top in this way, this is one way. I can also make the background dark. This is it with the background dark, and you'll see some very interesting patterns of color. I hope you can see them on the Zoom screen as well, or on the YouTube screen. So this is one way you can get objects. Well, there's not just plastic, any kind of plastic. So you often get very beautiful images with plastic spoons, forks, etc. Now with the lockdown, it's been very difficult to get plastic. Practically, they only give, you need a transparent plastic. But here's, for example, a transparent spoon. Okay, so we'll just line up a bunch of spoons. Let's keep some spoons like this. 1, 2. We'll keep a different type of spoon. Okay, here are a bunch of spoons. Nothing spectacular, right? Now let's put the second polarizer.
Wow.
How does that look?
Turn it slowly or not?
Okay, now shall I turn the polarizer? Okay, I'll turn the polarizer and keep it at this angle. Now you see different colors. I'll turn the polarizer and keep it at this angle. See different colors. I'll turn the polarizer, keep it at another angle. Now you have different colors. And go back here, should be dark field again. The outside is dark. The spoons are showing the patterns of stresses in it. You can see near the corners, typically the stress is the highest. So polarized images like this are also used sometimes to find out defects in objects, etc. To look at stress embedded in the thing, which you cannot see with normal light. And of course, you can make it more fun by just randomly placing pieces on top of each other. So if I just put some pattern like this and then put it, you will again get some very interesting random pattern. And you can see that at the junction, because the thickness is changing, you will get other colors as well. Okay, so we can make patterns like this. So let's just go and see if there are any comments on this and questions.
The protractor looks very nice, was one of the comments.
Okay, but by the way,
why don't we make some modern art?
Yeah, why don't you guys do some modern art?
Picasso.
Yeah, so this is can you see I'm holding a plastic bag? This is just a plastic bag, and this is a plastic bag on the thing, and now we keep the polarizer on this. And just look at comments. Why don't we do this and give the commentary?
Wow, it's like someone just painted the plastic thing, no?
Yeah, and now rotate the polarizer.
So you can find the Picasso in yourself. Focus करो
It's
जरा.
not focus. Can you focus it?
Focus करो.
नीचे
नीचे रखो.
नीचे रखो.
Yeah.
Focus.
Again, go.
Rotate.
Can you rotate it a little? No.
Yeah, rotate it
Put
slowly.
it
Yeah,
down.
that's
This
it.
way I'm focusing.
That's it. Yeah, remain there. Leave the thing there.
Yeah.
So you can see the stress patterns due to crumbling of the bag.
Yeah.
It's a two-layered bag.
And press it down again.
It's not that.
Okay. There, it's looking greenish and bluish. And at this point, it's probably reddish and purplish.
Yeah.
So you get all kinds of really interesting colors in polarized light. And yes, the Nehru Science Center, who are also online and watching this, say that you can buy these polarizers in the market as well. But these are just the ones made from our junk sheet. Now, this is a plastic bag. What if you want to make some art? One thing you can do, very simple thing you can do is take a glass slide. Okay, so here are two glass slides. Two glass slides. Come closer and get me the tape. And you can either use Scotch tape. You can either use. Can you just look at me? Yeah.
Yeah.
So you can either use Scotch tape or you can use normal cellophane tape. Okay, and some transparent object. Okay, so let's start with some tape. Can you just take this out? Meanwhile, I'll do Scotch tape. So I'm just going to take pieces of Scotch tape. Huh? Yeah, I'll just join them. I'll just join them. I'll join them at some funny angle. That's one Scotch tape. And that's some other Scotch tape. And now we're just going to go wild and just stick Scotch tape randomly on this. Third Scotch tape. Fourth Scotch tape. So now you are becoming your own artist. Just take some Scotch tape, put it up, overlap it. Okay, so we put some layers of Scotch tape.
Nothing enough.
One more for good luck. No, nothing. Arey yaar, second polarizer to chahiye na? So now, what happened? What kind of Scotch tape? I think we should use a cellophane tape. Wait, this is some. I don't know where the Scotch tape came from. Okay, we'll redo this with cellophane tape. Wait. So you need tape which. Okay, redo. Cellophane tape. Nikalna?
Yes, camera.
Okay, give me this. Okay, here is a piece we made yesterday. This was a piece. We had a plastic block with these cellophane tapes on it. And if you hold this between polarizers, you can see the tapes now. And if I turn the polarizer, you see how the colors change? See how the colors change? You get yellows, pinks, oranges, a little green spot here, changes. Becoming bright again outside. Now some other part in the middle, this has become pink and other colors. That color changes. So every time we change the angle of the polarizer and the analyzer, the two sheets, we're keeping one fixed, we're only moving the others. You can see how the Scotch tapes are becoming visible, and depending on where you overlap, you see different thicknesses, and you get this. Okay. You have a scissor? Nope. How's this plastic bag? Oh yeah, any plastic bag is good. That's some other small plastic pouch in which the spoons were kept. And you can see it looks very interesting
in cross polarized light. Okay, we have our cellophane tape. So here are our glass slides, and yeah, keep pairing. Easy. Here's one piece of cellophane tape. Let's just make sure this is going to work. I'm just going to put two and make sure that it works. Where's the polarizer? No. It's working, but okay, there is some effect clearly, but we need lots of these. Lots of these, and these are very thick. What you peeled off is many layers together, so it's actually not single layer. That's the end. Okay. We will not waste more time on this. We'll try and do something else. Continue with experiments. We'll figure out the sellotape one in a bit. But as you can see, if you have sellotape, you can actually get very nice patterns with polarized light. Okay, what's next? Time for questions, I guess. We're almost out of time. Okay. If people have questions, if you should repeat something. Actually, the Scotch tape dispenser sometimes also looks so nice. Oh, but this has got the Scotch tape in it, so that won't work. You need an empty one. The empty one looks good. Okay. I'm going to take a look at questions. Do you have a scissors? Yeah, one question is what is there in this sheet and how does it work? So can we get the room light on? I'll answer that. I'll come here. So what is there in these sheets? So one of the questions which has come in, and I'm sure it's there in many people's mind, is what is there in a polarizer sheet? Now clearly, you need something which interacts with light. And light has an electric field. So it has to be something which interacts with an electric field. Okay, not just absorbs the light. Okay, it will absorb some of the light clearly. So mostly, the most famous sheet used to be called Polaroid. Okay, Polaroid was invented by Edwin Land way back in the 1920s. And of course, he later on went to make cameras, which is why you have Polaroid cameras. But Polaroid cameras have nothing to do with Polaroid sheets. These sheets, which are called polarizers or Polaroid, are plastics. Basically, plastics. Plastics are long molecules. They are like, spaghetti or what do you call noodles, Maggi noodles. Now, normally, if you have Maggi noodles, it's all these things going on in every direction. But suppose while the plastic was melting, you pulled it. Then all your noodles are likely going to be stretched in one direction. Now you've built, let it cool down, you solidified it. Now your polymers are all aligned in one way. Now you have a sheet of plastic which is going to behave differently whether your light is coming with electric field this way or that way. Now, of course, plastics are not conducting. You wanted to interact with the electric field. So what they do to make Polaroids is earlier they used to put some other elements like iodine, etc. to dope it. These days, most of the modern Polaroids actually use silver nanoparticles, very tiny particles of silver, which are actually rod shaped. So the particles of silver are rod shaped and they're all aligned in one particular direction. They behave like this fence that you saw, allowing light only to go in it of one polarization to go through. So that's how you make most of these Polaroid sheets. You can also make them with different polymers. Some of the new polymers there are many. Chemists are fantastic people. They can make all kinds of molecules with interesting properties, and some of these are anisotropic by themselves. So, but mostly you sort of stretch it and you align the polymers so that the plastic is anisotropic. That's what happens. Okay. Other questions, please? Other questions? In fact, people can come here and I look at the questions and see what questions are there, and we can take them. Yeah. Are there any experiments which we've forgotten to do?
No.
No. Okay. And we've shown you how to remove the polarizing screen. In fact, these small pieces of Polaroid, the small pieces, often, in fact, mostly, it's very rare that we can pull off the whole sheet like this. Suryan uncle has years of experience of breaking these old screens. He can sometimes do it, but mostly it's so thin, this glass, that the thing breaks off, as you can see here. When it breaks off, of course, that's fine. You just use it to peel it off and make smaller pieces of Polaroid. Okay. What kind of questions do we have?
It's somewhat better from the.
Can you pick up from the camera directly?
I'll turn it. Just see whether it can.
Wait,
It's too bright. It's too bright.
Wait, get it closer.
Yeah, yeah.
Ah, okay, that's better.
That's it.
Now you turn the polarizer. Yeah, turn it slowly. See the center, how it went from blue to, oh, that's, you're getting the main light through it.
Yeah.
Right, that's okay. Some parts will always be bright.
Yes.
At some angles, all the light goes. And there, you can see that these colors in Scotch tape films are very nice. Okay, one question coming in is, why do we see different colors when you have these sellotape films? Now, remember that when you have a piece of sellotape, okay, this tape was stretched and rolled around something. So there is an inbuilt stress in this, which means that this film itself has properties which are different in different directions. And then when you shine polarized light to it, it's going to bend it slightly differently. And different wavelengths will be bent slightly differently. When you take multiple pieces and lay them across each other, the thickness is different. So the amount of rotation of this light is going to be slightly different. So they're all going to be coming, when it comes to the outside this material, different rays of light which have gone through, their polarization has been turned by a different amount. And then you're putting an analyzer on it, which is selectively going to block or reduce the intensity of light going through. And you will see some colors more prominently than others at different angles. Some colors come through, other colors don't come through. That's what you see as this very beautiful images that you saw. Okay. Any other questions? On Facebook, are there questions? Divya, if you're monitoring Facebook, can you just look at it and tell if there are questions?
Most of the question I have answered. One thing is how polarization was discovered.
How was polarization discovered? Good question. I really don't know. I think polarization was discovered probably in microwaves before light. I'm not so sure. I will look it up and tell you. I don't want to give you a wrong answer. I haven't really looked at the history of who discovered, how discovered, etc. We'll look that up. Okay, you can also go to Google or something and try and find out the history of polarization. Of course, many people have used, people knew that if you took a polarizer and made a filter with it, it worked very well to darken the sky if you're taking a picture, even in the days of black and white film. I don't know the history exactly. All right. Other questions? YouTube? Zoom? Okay.
So here's one question.
Yeah.
Is cellophane tape birefringent?
Is cellophane tape birefringent?
Yeah, cellophane tape.
Cellophane tape.
Normal tape.
Normal tape. Is this tape birefringent? Good question. I really don't know. Something I would have to check up.
You can put it here. Maybe.
It's probably going to be difficult. It's so rough that it's unlikely to. The good thing with the crystal, it's easy to see the two beams because the crystal has very nicely flat facets of the crystal. I don't know about the cellophane tape. Okay, other questions? Krishna is monitoring them.
So there are a couple on Zoom call.
Okay,
so
go ahead.
Are there any other material which shows double refraction other than calcite?
Are there materials which show double refraction other than calcite? All you opticists? I'm sure there are, no?
Yeah.
You know any?
So there is a question, can we do something with 3 polarizers?
Can you do something with 3 polarizers? I'm sure you can. I'm sure you can. You can take it. Come on, you can put 2 polarizers and we have smaller polarizers on top and we'll see what happens. Let's just put it. Let's just take our set square or something. So I'll do this. Why don't you take your camera? No, we'll do the third on top.
Third on top.
Let's put the set square. Okay. Let's put the second polarizer. Get the camera on this. Okay, let's make it dark field so it's easier. Yeah. Okay, so now we have 2 polarizers and let's put a third. And you can see what is happening with the third. Can you see what is happening? In some places, you are again changing the colors you would get here, of course, this is not too bright. So
we can do one more thing.
See, okay, let's go close. You can see the colors. Now, you'll change, you see the color, remember the colors, and the colors will again change because I have one more polarizer on top. There will be some positions where it will behave differently. So yes, you can put many polarizers.
Yeah,
Without,
one more thing.
do it without a set square. Do it without a set square.
Yeah,
Set it
you can just do it without the set square.
Yeah. And now you put the third one.
Yeah. So
Yeah,
dark. So effectively, the combination of two polarizers is giving you some polarized light, and then the second, whatever you put outside, is going to interact with that polarization. So I can either do this or I can change the middle one now. I can move the middle one, and that will also change the intensity of the light. You can either change the middle one, or you can change the top one, or you can change the bottom one. That's a little bit more difficult to change it over here, but you get the idea. All right. Other questions?
All three speakers go back.
You guys can go there and check questions. I will check this. Anything else? Have we missed something? Okay. So, okay, looks like there are no more questions. We are out of time. So let's get our three presenters here, and we should thank Kiran for coming in absolutely last minute this morning and substituting for Surabhi. Surabhi, I hope you're listening to this. Thanks so much for helping us with arranging all of this. Sorry you're in a quarantine. And just remember that we're still not done with COVID, so you have to be careful. If you are eligible for a vaccine, please try and get one or two after survive. And otherwise, please wear a mask at all times, outside, interacting with people, and stay safe. We have many more experiments coming up, and a week from now, the first Sunday of June, we are going to be doing some interesting chemistry experiments. Our chemistry team is going to be here, and they will show you some fun experiments as well. Till then, be safe. Watch other recordings of China if you want. Thank you so much for watching. Bye for now.